Hello everybody, my name is Kyle. Today we're going to be doing part 2. We're going to be doing hopefully 15 more problems, as many problems as we can. And yeah, let's get right to it. So problem number 16 says, on an alien planet OZ3812, an object moving at 4 meters per second on the horizontal ground comes to rest after traveling a distance of 10 meters. If the coefficient of kinetic friction between the object and the surface is 0.2, what is the value of g on this planet? Okay, so there are two ways of solving this. The first way of solving this is by using kinematics, and so we'll do that first. So this is the box. It's moving to the right. We are going to draw the normal force. This is just the normal force body diagram. This is the frictional force, Fk. And we have weight here, W. Now, it's moving this way, and we're trying to find is gravity. Okay, so the sum of the forces in the x direction, sum the forces in the x direction is equal to ma. It's slowing down, so acceleration is not equal to 0. And there's only one thing in the x direction. There's only one force, and that's F of k. Now F of k is equal to the frictional force, which is equal to mu times the normal force. Now, what is the normal force? So if we look here, we can see that the sum of the forces in the y direction, let me make this more clear. This is the x direction. That's the y direction. The sum of the forces in the y direction is equal to 0. It's not falling through the floor, so it's equal to 0. No acceleration in the y direction. This is equal to, if we say up is positive, F of n, which is the normal force, minus W. So it's obvious that the normal force is equal to the weight. So weight, in this case, is mg. So if we're trying to solve for this, let's just keep subbing things in. We would say this is equal to mu mg. The other thing that we have to remember from kinematics is that v final squared is equal to v initial squared plus 2 times the acceleration times the change in x. Now, one of the things that they've told us is that the change in x is 10 meters. Mu is equal to 0.2. Let's see. What else does it say? V initial is equal to 4 meters per second. And that the mass, does it give us some mass? No, it doesn't give us a mass, and I don't think we need it. Okay. Now, we know that v final is equal to 0. That v initial squared 2 over 2 delta x is equal to a. So now it makes sense that the acceleration is negative because it's going in the left direction. So continuing on, we're going to sub all of this into this equation. So we have ma is equal to m times acceleration, which is negative vi squared over 2 delta x is equal to mu mg. So the nice thing about this is that the masses cancel, and if we're just looking for g is then equal to negative vi squared over 2 delta x mu. So we're going to keep that because now we're going to solve this using energy. So this is solving it using kinematics. Let's go ahead and get our eraser. Okay, so if we're going to solve this using energy methods, we would need a final and we would need an initial. So in the final state, we have all of the energy being dissipated into friction. So I'm going to call that friction F. And the initial state, we have just kinetic energy. So basically all the kinetic energy then becomes frictional energy. Your teacher may have called this frictional energy non-conservative work, NC. All right, so let's go ahead and write this down. So we have 1/2 mv squared then equals negative mu mg d, and the masses cancel out, thankfully for us. And if you want to just find g, it then becomes negative v squared all over 2d, and we have mu. And this is the same as this. So if you use kinematics, you'll get pretty much the same answer as using the energy methods. Let's read number 17. Number 17 says, a 2,000 kilogram truck drives up a hill that makes an angle 15 degrees with the horizontal. What is the work done by gravity on the truck if the distance it travels is 100 meters? Most people would just jump the gun and say, oh, work is equal to FD, and say D is 1,000 meters. But we have to be careful here. So if we actually draw it out, there is a ramp, and the angle is 15 degrees. And we start here. This is our initial, and this is our final. Because it's traveling up at an angle, we have to use cosine of theta. So the answer is actually f d cosine of theta, where theta is equal to 15 degrees. F in this case is equal to the gravitational force, which is equal to mg. Now, there's one more trick to this problem, in that it's asking for what is the work done by gravity. So the work done by gravity is negative. So the reason that the work done by gravity is negative is because usually gravity takes things and brings them down. But in this case, the truck is moving upwards. So that's why the work done by gravity is negative. Okay, next question. Number 18. A mug rests on an inclined surface which makes an angle of 14 degrees with a horizontal. What is the magnitude of the frictional force exerted on the mug? B. What is the minimum coefficient of static friction required to keep the mug from sliding? So if we draw this out, we have an angle here, 14 degrees. We have the mug. We have weight here. And then we also have friction, F of S. And then we also have the normal force. F of N. The first question is asking for the magnitude of the frictional force exerted on the mug. So we have defined F of S. So we could try some of the forces in the x direction. So because the mug is static, we know that the sum of the forces in the x direction, x, is equal to 0. And that is equal to, if we make going this way positive x, that is equal to minus w. Now this is not just w, this is the x component of w. So how do we find the x component of W? So we have our angle here, and if you remember that this angle equals this angle right here, now we could basically write down sine of theta is equal to opposite of our hypotenuse. Opposite is what we're trying to find, the x component of weight over the hypotenuse, which is W. F of S is equal to Wx, and Wx is equal to W sine of theta, where W is equal to mg. So that's part A. Now for part B, we have to find the minimum coefficient of static friction. So in order to solve for the minimum coefficient of static friction, we can combine the forces, our equation for the forces in the x direction and the forces in the y direction. Now I'm not completely sure why this works, but I'll just show you the process anyways. So we have some of the forces in the y direction is equal to 0 in this case because it's static. And in this case, we're going to make up as positive y. F of n minus the y component of weight. So the y component of weight is equal to cosine theta times W, where W is equal to mg. So the normal force is equal to mg cosine theta, where theta is 14 degrees. So we can sub this back into the sum of the forces in the x direction. So we've already written that down up here, and then we found out that the static frictional force is equal to the weight. So we could write all that down. F of S is equal to mu times the normal force. Normal force is mg cosine theta. And this is equal to the x component of weight, which is equal to mg sine of theta. Now the nice thing is that the mg's cancel out, and if we divide both sides by cosine of theta, we'll find that the minimum coefficient of static friction, which is mu, is equal to tangent of theta, where theta in this case is equal to 14 degrees. Now for number 19. Okay, so now for number 19. Two blocks stacked one on top of the other can move without friction on the horizontal surface shown in the figure below. The surface between the two blocks is rough, however, with a coefficient of static friction equal to 0.47. If a horizontal force F is applied to the 5 kilogram bottom block, what is the maximum value F can have before the 2 kilogram top block begins to slip? So we have a horizontal smooth surface, and then we have two blocks, one here and one here. So this is 5, and the other is 2, I believe. Yes. Now, the surface here is rough between the two blocks. Now, if you know that this picture is basically equivalent to this picture, we can solve for the answer immediately. Go ahead and finish writing. So what's happening in the left is basically what's happening on the right, where we have a rough surface here, we have a 7 kilogram mass, and then we have a smooth surface down below. Now the reason these two are the same is what actually happens is when we move the bottom block with enough force, there is inertia here on the top block. And the top block basically acts like a surface that doesn't move. So that's why this over here turns into this. We can draw our force body diagram. So there is this force, and there is the static frictional force. So because the problem says that this is just before it starts to slip, the sum of the forces in the x direction are equal to 0. So this is just before it starts to move. And just before it starts to move, it's still static. So this is equal to, if we make this positive x, F minus the static frictional force. So basically, F is equal to F of S, which is equal to mu times the normal force. And the normal force in this case is equal to mg. So F is equal to mu mg, where m is equal to 7. Okay, so now let's read number 20. A 35 Newton bucket of water is lifted vertically 3 meters and then returned to its original position. How much work did gravity do on the bucket during this process? Now, because it was lifted and then returned to its original position, the work is 0. So that's just something to remember. If something returns to its original place and you're asked how much work in total has happened, the answer is always 0. Okay, so number 21. A traveler pulls on a suitcase strap at an angle 36 degrees above the horizontal. If 555 joules of work are done by the strap while moving the suitcase a horizontal distance of 15 meters, what is the tension in the strap? We have our suitcase over here. Let's add some wheels. And then you have this. So this angle is given to us, I believe. Yes, 36 degrees. So this is 36 degrees. And does it tell us anything else? It tells us that the amount of work done was 555 joules. And then it also says that the horizontal distance is 15 meters. So let's go ahead and write that down. 15 meters. So our equation for work is equal to force times the distance times the cosine of theta. We have theta given to us as 36 degrees, distance as 15 meters. Work is 555 joules, and now they're asking us to find tension. And so that's pretty much all you have to do here. You just have to rearrange the variables to find force, or in this case, tension. So tension is equal to work over distance times the cosine of theta. All right, so let's go ahead and look at problem number 22. So it says, driving in your car with a constant speed of v, you encounter a bump in the road that has a circular cross-section, as indicated in the figure below. If the diameter of curvature of the bump is 104 meters, what is the maximum value of v so that you do not fly off the road at the top of the bump? So I need to show y'all the picture. Here it is. So what it's asking for is, what is the maximum velocity of the car so that you do not fly off the bump? Here we go. Here is the bump. Here is the car at the very beginning. It's going up with a velocity v. Now, the interesting thing to note is when it's at the top, there are only two forces acting on this. In this ideal situation, there is the weight of the car, W, and then there is this other thing called centripetal force. Because this is a circle, it goes up. Once it reaches the top, there's centripetal force. Now, to find the maximum velocity, you would have to make this equal to this. You'd have to make the centripetal force equal to the weight. If the centripetal force was greater than the weight, it would fly off. If it was less than the weight, it would still stay on the bump, but what it's asking for is the maximum velocity. So these two would be equal to each other. So centripetal force is then equal to the weight. So the equation for centripetal force is equal to m times a, right? Force is equal to mass times acceleration. Acceleration in this case is equal to v squared over r, where r is the radius. Weight is equal to mg, and in this case, the m's cancel out. We're trying to find velocity. Do we know the radius? No, we don't, but we do know the diameter. And if you remember, diameter divided by 2 is equal to the radius. All right, so let's do number 23. Number 23 says, a stone with a mass of 1 kilogram is tied to the end of a light string, which keeps it moving in a circle with a constant speed of 4 meters per second on a perfectly smooth horizontal tabletop. The radius of the path is 0.6 meters. How much work does the tension in the string do on the stone as it makes 1/2 of a complete circle? What we're trying to find is work. Work is equal to force times distance times the cosine theta. Now, what's actually happening is you have this stone, this is the string at the very beginning. It makes a half circle, right? It goes all the way around. This is where it ends up, right? Goes this way. Now this could be a little challenging because what does it mean for work in this case? Now, we have to simplify the problem just a little bit. So what we can say is if we just look at this part and we look at this part, they're going at opposite directions. So the distance is the same. See? Distance, distance, but they're in opposite directions. Now the work over here, we would call it, so let me go ahead and get my eraser. So if we had work, we would call this W, positive W, if we have the direction going here. If we say this is positive X, this would be positive work. And for this one, it would be negative work because the distance is the same and the tension is the same. This W would be equal to that W. The only difference between this W and that W is the theta. So over here, theta would be 0 degrees, and over here, theta would be 180. So these two would cancel out. Okay, so that's for the case of for the work that's on either side. Now, what about this case? So if you look at this case and this case, it would be the same. This would be W, and this would be positive W, and this would be negative W. And these would cancel out. Same for this. This would be positive W, negative W. Now, the only tricky part is the one in the middle. So this, the one in the middle, actually has a tension, right? T has a tension. But the distance, in this case, it would be going up. But because we're measuring things only going left and right, the distance would actually be 0. Additionally, if you look at cosine of theta, theta in this case would be 90 degrees. And cosine of 90 degrees is also 0. So for the case of the stone being in the very middle, it would also be 0. So if you add all the work up, it would actually equal 0. So there's actually no work done here. So let's go ahead and look at number 24. How much work is required to stretch an ideal spring of spring constant 40 newtons per meter from 0.2 meters to 0.25 meters if the unstretched position is at 0 meters? The work of a spring is basically the same units as energy of the spring. So If you remember your equation for the energy of a spring, I'm going to denote it as S. So this is the spring energy. S is equal to 1/2 kx squared. 1/2 kx squared. Now, usually people would start at the tricky part about this is some people would be tempted to say, oh, if we just, the first thing we have to do is subtract it. 0.25 meters minus 0.2. That would give us 0.05 meters. And then we just plug in for x. We already know k because given in the problem k is equal to 40 newtons per meters. But if we do the problem like this, it would be wrong. The reason you wouldn't subtract is, this is how to find the energy of the spring if it started at 0.2, right? If it started at 0.2. And it doesn't really start at 0.2, it starts at 0. In fact, the problem states that quite clearly. It says the unstretched position at x is equal to 0. So the way to actually do this problem is you have to have a final energy, and then you subtract it from the initial energy. Final is 1/2 kx squared, where x is 0.25, minus 1/2 kx squared, where x in this case is 0.2. And that change in energy is equal to your work. This isn't the same as doing this because there's this squared here. And if you don't believe me, you can put the numbers in. But if you use this equation, this will give you the right answer. Let's go ahead and look at number 25. An object hits the wall and bounces back with half of its original speed. What is the ratio of the final kinetic energy to the initial kinetic energy of the object? Initially, the energy is kinetic, 1/2 mv squared. So let's denote this as 1. The velocity initial, vi squared. The final is equal to 1/2 mv squared. In the final situation, we only have kinetic energy again. No, we don't have any potential energy. It doesn't tell us the height or anything like that. It only has kinetic energy. Now, what does it tell us about this v final? This v final is equal to half of its original speed. So vf is equal to 1/2 vi. Now, it's asking for the ratio of the final energy to the initial energy. So it's asking for final over initial, looking for the ratio. Ratio is another word for fraction. All we have to do is sub all of these values in. So this is 1/2 m vf. So we already know that vf is equal to 1/2 vi squared. So we could just sub this in to here. This is 1/2 vi over 2 squared, all over the initial, which is 1/2 mvi squared. And this cancels out with this, and we would be left with vi squared over 4 all over vi squared. The vi's cancel out, and you're just left with 1 over 4. Let's look at number 26. A sled having a certain initial speed on a horizontal surface comes to rest after traveling 10 meters. If the coefficient of kinetic friction between the object and the surface is 0.2, what was the initial speed of the object? So there's a smooth surface, then there's like this rocky surface, and then there's a smooth surface. Initially, it's traveling with a speed v, and then after a certain amount of time, it doesn't reach the other side. It just stays in the rocky place, so to speak, and then it stops after 10 meters. So this is 10 meters, 10 meters. And the coefficient of friction here, mu, is equal to 0.2. 0.2. Okay, so what it's trying to ask for is V. Can we find V? Question mark. So we have basically all of the kinetic energy being transferred over to frictional force. Or you can also think about it as the same thing as non-conservative work. W and C. Again, this non-conservative work can be set as FKD, where this is the frictional force times the distance, because work is equal to force times distance. And this frictional force could be represented as mu mg, or mu times the normal force. Kinetic energy is equal to 1/2 mv squared. So we just pop in the distance, and the nice thing about this is the masses cancel out, which is good because they didn't give us a mass. And what we're trying to find is a velocity. So in this case, velocity, I don't know why I'm changing colors, but why not? Velocity then is equal to 2 times mu times gravity times the distance. All right, number 28. The figure below shows a 1.75 kilogram block at rest on a ramp of height h. When the block is released, it slides without friction to the bottom of the ramp and then continues across a surface that is frictionless, except for a rough patch with 10 centimeters that has a coefficient of kinetic friction uk of 0.64. Find h such that the block's speed after crossing the rough patch is 3.5 meters per second. Something that goes like this, and then there's a rough patch, and then there's something smooth. Starts here, goes down. This potential energy becomes kinetic energy, and then some of it becomes non-conservative work or friction, and then it keeps going on with V is equal to, what is it? 3.5 meters per second. 3.5 meters per second. All right. So we need to find height, h, right? So this potential energy gets converted into kinetic energy, where V is equal to 3.5, plus some frictional energy, Fe. Okay, so let's go ahead and write this down with actual proper symbols. So potential energy is equal to mgh, kinetic energy is equal to 1/2 mv squared, plus the frictional energy, which is equal to mu k times the normal force, mg, times the distance, d. So are we given distance? Yes. Distance here is 10 centimeters. We have to convert it into meters, so that becomes 0.0. No, it becomes 0.1, sorry. I was thinking about it. I was like, nah, that doesn't sound right. Yeah, 0.1 meters, right? Gravity, we always know. The masses cancel out. Thank you. Masses cancel out. And then, do we know height? No, that's what we're looking for. Do we know V? Yes, we do. It's 3.5. So basically, all we have to do to find height is take 1/2 v squared plus mu k times gravity times the distance, divide it by gravity, and that will give us the answer. Moving on to question 29. 29 says, in a ballistic test, a 28-gram bullet pierces a sandbag that is 30 centimeters thick. If the initial bullet velocity was 55 meters per second, and it emerged from the sandbag moving at 18 meters per second, what was the magnitude of the friction force, assuming it to be constant, that the bullet experienced while it traveled through the bag. We don't have a smooth surface anymore, but we're assuming that there's no gravity, so it's kind of on a smooth surface. So here's our bullet. It goes through the sandbag. And then it emerges on the other side with a velocity equal to 18 meters per second. So this is 18 meters per second. This is velocity final. Velocity initial is equal to 55 meters per second, right? Yes. 55 meters per second. The mass stayed the same. Mass is equal to, what is it, 28 grams. So we have to convert that into kilograms. So that's 0.28 kg. Basically what we have is we have kinetic energy, which then gets converted into frictional force, frictional energy, plus kinetic energy, because there's still some kinetic energy here. So all we have to do is just write that all down. So we have 1/2 mv initial squared is equal to the frictional energy as F. We're being asked for the frictional force, right? So we don't know. This isn't mu k mg because it's not on a flat surface, but it's fine because we're actually being asked for the frictional force, kinetic force. Do we know the distance? We know that the distance is 30 centimeters thick. So to convert that to meters, that's 0.3 centimeters thick, plus the kinetic energy again. But in this case, it's 1/2 mv final squared. So the masses don't really cancel out, but it's fine because we know the mass is 0.28 kilograms. And so all we have to do to find the frictional energy is isolate it. So we have Fk is equal to, that's my dog, if you can hear her, mvi squared minus 1/2 mv final squared divided by the distance. And that gives us f of k, which is what we're looking for, the frictional force. Number 30. An ideal spring stretches 21 centimeters when a 135 Newton object is hung from it. If instead you hang a fish from this spring, what is the weight of a fish that would stretch this spring by 31 centimeters? So, case 1. We have a spring. It's a certain length, and then we have a mass. Case 2, we have a heavier mass. It's the same spring, but the length is longer, the mass is bigger. So in the first case, we know that the distance is 21 centimeters. So we have to convert that to meters, so that's 0.21. Right. The mass, do we know the mass? No, we don't know the mass, but we know the weight. So the weight in this case is 135 newtons. In this case, we know that the distance is 31 centimeters, or 0.31 meters. We don't know the mass, and that is what we're looking for. If we do some of the forces around this point here, in case 1, we'll find that these two are in equilibrium. We're assuming that everything is static, so that means that in the y direction, the weight is equal to the force of the spring. So the force of the spring is equal to kx. That is equal to mg. Now the only thing that we don't know is k, right? If we don't know k, we know x, we know m, we know m and g. This is 135 newtons. But we don't know k. And that's the one thing that we know stays the same between case 1 and case 2. In case 1, the K, the spring constant for the spring, is K, and in case 2, the spring constant of the spring is still K. So if we don't do anything to the spring, like we don't cut the spring, we don't do anything to the spring, if we just hang another weight, the spring constant stays the same. So what we want to do is we want to find K. And in this case, we know X, we know K, we can solve for the weight, which is what we're actually looking for. So mg, which is what we're looking for, is equal to K, which is the same as before, and then X, which in this case is 0.31 meters. And that's how we solve for mg. Okay, as a bonus, we can do a few more questions. So this is question number 31. Let's go ahead and read it. So a block slides down a frictionless inclined ramp and experiences no significant air resistance. The ramp angle is 17 degrees above the horizontal, and the length of the surface of the ramp is 20 meters. Find the speed of the block as it reaches the bottom of the ramp, assuming it started sliding from rest at the top. So we have this, and we have something at the top, and it's sliding down, and we're trying to find, what are we trying to find? Speed, right? Yes, we're trying to find speed. So this V is equal to a question mark. So we can use energy methods here. This can be really easy using energy methods. Now we know that theta is equal to 17 degrees. 17 degrees. And we also know that the length of this ramp here is equal to, what does it say? Is equal to 20 meters. So 20 meters. Now, if you used energy methods, we can say that the ramp, or I'm sorry, this block started at a certain height, h, right? And all of the potential energy gets converted into kinetic energy. So, what color did I use? This one? Okay. Nope. mgh is then equal to 1/2 mv squared. Now, the masses cancel out. Do we know g? Yes, we do. Do we know h? We can solve for that. Do we know v? That's what we're looking for. Let's just go ahead and solve this for v really quickly. V is equal to the square root of 2 times gravity times the height. Now, do we know the height in this case? No, but we can use really simple trig to solve for it. This is theta. What we're looking for is over here, h. We know this is 20 meters. So we can say sine theta is equal to opposite over the hypotenuse. Opposite is height. Hypotenuse is 20. And then once we solve for height, we could just plug it back into this equation and solve for velocity. All right, hopefully you found that helpful.